Hello, am I audible and is my screen visible?
Yes, sir.
Okay, thank you. Yes, you can mute yourself. Good evening, everyone. Welcome to this NPTEL live session for the course Introduction to Machine Learning. My name is Zawan Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. Uh, in this live session, we will discuss some practice problems on week 5 topics, which were mainly artificial neural networks and some topics on parameter estimation as well. So we will discuss some questions on these two topics, artificial neural networks and parameter estimation. And if you have any questions or queries on these topics, you can ask me during this session. So we will start solving some practice problems first, and if there are any other questions or doubts on these topics, you can ask me after discussing these practice sessions, the practice problems. This is the first question. Which of the following are correct? Multiple options may be correct in this question. First option says that a perceptron will learn the underlying linearly separable a perceptron will learn the underlying linearly separable boundary with finite number of training steps. Option B says XOR function can be modeled by a single perceptron. Option C says backpropagation algorithm used while estimating parameters of neural networks actually uses gradient descent algorithm. And the last option is the backpropagation algorithm will always converge to global optimum, which is one of the reasons for impressive performance of neural networks. So multiple options may be correct in this question. KR Shanmuga Priya says is the problem solving. Yeah, all the problem solving session video recordings and these slides or materials are already uploaded, and you can get the links in the course homepage. You have a tab called problem solving sessions on the left hand side in the NPTEL portal on this course webpage, and all these recordings, video recordings are uploaded in YouTube, and through those YouTube links you can access these sessions, and these slides are also there. Muthu Kumaran Iyer says option A. Sweta Lakshmi says option A and C. Okay. KR Shanmuga Priya says option C. Any other answers? So multiple options may be correct in this question. Okay, so the first option says that a perceptron will learn the underlying linearly separable boundary with finite number of training steps, and this option is correct, and it is theoretically provable also that if the classes are linearly separable, then the perceptron learning algorithm will find the separating hyperplane or boundary within a finite number of steps. So this option is correct. Second option says XOR function can be modeled by a single perceptron, which is not correct, and it is easily visible that in XOR functions the 4 points are positioned on the 2D plane in such a way that you cannot separate the positive points from the negative points, or the 1 points and 0 points using a single straight line. So and a single perceptron will always create a linearly separable boundary or a straight line to separate the two classes. So a single perceptron will not be able to classify those 4 points that are produced by XOR function. Option C says a backpropagation algorithm used while estimating parameters of neural networks actually uses gradient descent algorithm. This is also correct. So it basically uses gradient descent algorithm, and backpropagation, the specialty in it is that it propagates the gradient value backwards, starting from the output layer to the input layer, but the underlying algorithm is simply the gradient descent algorithm. Option D says that the backpropagation algorithm will always converge to global optimum, which is one of the reasons for impressive performance of neural networks. This is not correct, and the backpropagation algorithm in a neural network might get stuck at a local optimum, and it might never be able to get out of that local optimum point, and it might not be able to converge to a global optimum. So this is a known problem in backpropagation. So if the loss function or the objective function in that neural network for that specific problem is such that there are multiple such local optimum points, then it might happen that backpropagation will get stuck at a local optimum point, and it might not be able to get out of that and reach the global optimum. So this option is wrong. So the correct two options are A and C. Now question 2. So this is simply the XOR function table. So recall the XOR table example from the class where we did a transformation of features to make it linearly separable. Which of the following transformations can also work? So we want to transform these two features x1 and x2 in such a way that and this y is the target level and x1 and x2 are the two features. We want to transform x1 and x2 in such a way that these 4 points become linearly separable. There are two classes we can see, -1, so this -1 and these are +1 points. So we want to transform the input features x1 and x2 in such a way that the points become linearly separable. Originally these XOR function data points are not linearly separable. So there are 4 different transformation options given in A, B, C, D, and so you have to check each of the transformations one by one and find out whether a certain transformation makes these points linearly separable or not. So has anyone found out the answer? So in this question you have to try out each of these features separately, sorry, each of these transformations one by one, and check whether these transformations make the 4 data points linearly separable or not. So we will try out the first transformation. So first one says that x1 dash equals x1 square, x2 dash equals x2 square, and it is easily visible that it will make these data points it will not be able to make the data points linearly separable, because if we take the square of these points, all of these points would become 1. So all these points should become 1 comma 1. So if we compute the x1 dash x2 dash, all these would become 1 comma 1. So all 4 points will be at 1 comma 1. So the all the points would become indistinguishable from each other. So first transformation will not work. So now the second transformation. So second transformation is x1 dash is 1 plus x1 and x2 dash is 1 minus x2. So if we compute these two features, so for the first point x1 dash would become 0, for the second point x1 dash would be 2, for the third point x1 dash would be 0, for the fourth point x1 dash would be 2. Similarly we have to compute x2 dash, which is 1 minus x2. So first one is 2, second one is 0, third one is 1 minus 1 0, fourth one is 1 minus 1, so 0.
2, no? Second one will be 2.
Second one 1 minus minus, yes, yes, you are correct. Second one would be 2. So these are the 4 points. Now if we plot these 4 points, we will see that first point is at 0 comma 2. So 0 comma 2 somewhere here, and its level is given in y, which is minus 1. Second point is 2 comma 2, so somewhere here its level is 1. Third point is 0 comma 0, its level is 1. fourth point is 2 comma 0, so it is here, its level is -1. So we can see that it is the points are same as XOR. So these two are the negative points, and these two are the positive points, and we can easily see that we cannot draw a single straight line to separate the +1 and -1 classes. So this transformation would also not work. So the first two transformations would not work. Now if we compute the third transformation in the similar way, so third transformation says that x1 dash is x1 into x2, x2 dash is minus x1 into x2. So x1 dash for the first point would be just product of x1 and x2, so 1. Second point would be -1, third point would be -1, fourth point would be 1, and x2 dash is minus of x1 and x2, so it is -1, 1, 1, -1. Yeah, I hope I have computed all these values correctly. Now if we plot these values, so first point is 1 -1, so 1 -1 somewhere here, and its level is -1. Second point is -1 1 here, its level is +1. Third point is -1 1, so it falls on this same for as the first point, which is -1. Third point is 1 -1. Oh, sorry, this third point was -1 1, which is same as the second point, and the fourth point is 1 -1, which is same as this point, and level is -1. So we can see that, so these 2 points are positive points and these 2 points are negative points. So we can easily draw a straight line anywhere between these two set of points, and it will be able to linearly separate these two classes.
Sir, so basically there should be two classes, sir.
Yes, there are already given two classes, +1 and -1, for all 4 points. You have to check whether you can draw a straight line such that the two classes are separable or not. So in this third transformation, we see that the transformed points are such that the +1 class and -1 class can be separated using any many straight lines. I have drawn one such straight line that will be able to separate these two classes. And so third one will work. So first two didn't work, third one will work, and similarly you can compute the fourth one, and I think fourth one would also work, so it is computed here. Fourth one was x1 minus x2 square and x1 plus x2 whole square, and if you compute these two transformed features, you can see that these are the 4 points, and again if you plot these 4 points, you will see that the classes are linearly separable. So C and D, these are the two correct transformations that make the points linearly separable. Is there any doubt or query in this question?
So we need to just substitute the values in the formula and check whether they are
Yes.
separated into classes.
So these are the actual original feature values. You have to compute this transformed feature values from x1 and x2, and then plot those points in the 2D plane and check whether the two classes are separable or not.
So the obtained values of x1 dash and x2 dash are plotted.
x1 dash and x2 dash?
Are plotted in the graph and check whether
Yes,
they are
yeah. So you have to plot the transformed features x1 dash and x2 dash. Yeah.
Sir, what is XOR here?
What is
XOR.
so this table is for XOR function, XOR the logic gate function.
Okay, sir.
Can such type of question be asked for any other kind of like here it is asked linearly separable, so it is easy to identify, but कुछ और इसके लिए भी पूछ सकते हैं क्या?
No, linearly separable is generally, such questions are asked only for linearly separable points.
Okay.
If it is not linearly separable, you can basically classify any set of points.
Correct.
Whether it's you can draw any curve which is non-linear, that can classify any set of points, any two classes. But in case of linearly separable, you have to check whether you can draw a straight line or not.
और किसी के लिए मतलब ये भी नहीं पूछेंगे?
No.
Okay.
Now question 3. What is the effect of using activation function fx equals x for hidden layers in an artificial neural network? So the activation function is fx equals x. Basically, whatever is the value, the activation function returns that one. So identity activation function, you can say. And if this activation function is used in a hidden layer in a neural network, what is the effect of that? There are 4 options. No effect, it's as good as any other activation function like sigmoid, tanh, etc. The ANN is equivalent to doing multi output linear regression. Option C says that backpropagation will not work. Option D says that we can model highly complex non-linear functions. Sweta Lakshmi says B and C. Okay. Devasis says option B. Megha also says option B. Muthukumaran Iyer says option C. Pon Murugan Muthuswamy says option D. The correct answer in this question is option B. ANN is equivalent to doing multi-output linear regression. There is only one correct answer. The ANN is equivalent to doing multi-output linear regression. So if we use this identity activation function fx equals x, so whatever is the pre-activation computed value, the activation function returns only that. So the first option says that no effect, it's as good as any other activation function. This option is not correct. This is not as good as any other activation function because this sigmoid, tanh, even ReLU activation function, all these activation functions bring non-linearity in the structure of the neural network, so that it can create non-linear decision boundaries. But this fx equals x identity activation function does not bring any non-linearity in the neural network, so it will not be able to classify classes which are not linearly separable. So this identity function is not as powerful as sigmoid, tanh, these activation functions. Option C says that backpropagation will not work. Backpropagation will certainly work. Backpropagation just needs the activation functions and the loss function to be differentiable and continuous. So the fx equals x is certainly continuous and differentiable. So backpropagation calculation will work. And option D, so this option is not correct. Option D says that we can model highly complex and nonlinear.
No, why is it option C? And that connection went for a second. I couldn't hear that when you said. What? Why not option C?
So backpropagation needs the activation function to be continuous and differentiable, but and here the fx equals x is certainly continuous and differentiable. So backpropagation calculation will certainly work. There is no problem with backpropagation.
Okay.
And option D says that we can model highly complex and non-linear functions, which is not correct. It cannot model any non-linear function. It can only model linear functions. So because so if we apply such activation functions in a multi-layer neural network, what will happen is that first layer will compute wx if x is the input input matrix or input features. w1x is the output of the first hidden layer. Then we apply, there is no fx equals x basically means you are not applying any activation function. So if we had applied some activation function, it would have been sigma of w1 x1, then in the second layer it would become sigma of w2 of sigma of wx1. So this sigma is some activation function that you are applying. In our case, this sigma is basically not existent here. Sigma is identity function. So w1 x1 is the output of the first layer, first hidden layer. Then in the second hidden layer it simply computes w2 into w1x. In third layer would compute w3 into wx. So let's say there are only 3 layers, hidden layers. So this is the output, final output. So we can simply merge these 3 matrices into one, let's say w. We can certainly, because of the associativity property, we can merge these three matrices into one w. W is simply w1 into w2 into w3. So this becomes w into x. Thus it is no different than a linear regression method. So applying multiple layers does not make it non-linear in any way. It becomes a same as linear regression.
So for the first option, it is not correct because it is not as good as sigmoid and tanh. Correct, sir?
Yes. Yeah, it is. It does not bring any non-linearity in the neural network. Sigmoid, tanh, all these functions are non-linear. So and because of these activation functions, neural network has the power of creating non-linear decision boundaries. Otherwise, these matrix multiplications like w1x, which happens in the hidden layers before applying the activation function, does not bring any non-linearity. Non-linearity comes because of this activation function, sigma or tanh, whatever activation function you apply on the computed value.
Sir, so option A and D are correlated, so both are ruled out, sir.
Yeah, option A and D are, I mean, those two options are almost similar, that you cannot also build highly complex nonlinear functions using that. Yeah.
So can you explain B option once again?
So B, what I just wrote that if we apply, let's say there are after the first hidden layer it computes w1x, isn't it? And after that you are applying another hidden layer, so it computes w2 into w1x, and if there is another hidden layer it will compute w3 into the whole thing, w2 w1x. So you can simply combine these three matrices into one w, which is simply multiplication of these three matrices. So you can write it as w into x. So this is just linear regression. You are multiplying the input features with a weight matrix w. So it becomes w into x. Although you are applying three hidden layers and their weights are w1, w2 and w3, but you are not applying any activation function, practically no application function, because this fx equals x is doing nothing here. So it simply becomes equivalent to just having one one input layer, one output layer, w into x it calculates.
Sir, so the multi-output here means the W1, W2, W3 that we obtain, sir?
Multi-output basically means if we have multiple units in the output layer, So for example, in classification task you would have multiple classes, so multiple outputs might be there for different classes, and if there is only one output, you can have only one output as well. So basically it computes linear regression. It does not have any non-linear part in it.
Yes, sir. Got it, sir.
So is there any doubt in this question? Now question 4. Which of the following functions can be used on the last layer of an ANN for classification? Softmax, sigmoid, tanh, linear. So which of the following activation functions can be used in the last layer of the ANN for classification? Anagha Pankaj Chogaonkar says option A. Anantapalli Naga Lakshman Kumar says option A. Devasis says option A. Prakash Chandra Bhoi says option A. And the multiple options may be correct in this question. Muthukumaran Iyer says A, C. Onima Naik says A, B. Ansila VM says AB. Correct answers are A, B, C. All these three activation functions can be used in the last layer of an ANN for classification. So sigmoid softmax is simply defined as e to the power some xi divided by summation over e to the power xi over all the classes, and sigmoid is defined as 1 divided by 1 plus e to the power minus x or theta x, whatever it is. I mean, if x is the input to that activation function. Tan h is tan h is e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x, and linear is simply x. If x is the input, the output is x. So all these three A, B, C, these first three activation functions can be used in the last layer of an activation neural network for classification, because sigmoid is a very obvious choice for two class problems. If you have two classes, sigmoid is the most obvious choice. You would have only one hidden output unit, and sigmoid would give you the probability of being class 1. And softmax is used when you have multiple classes, more than two classes, then softmax is used. Tan h, the range tan h is very similar to sigmoid in its graph, but so instead of being ranging from 0 to 1, it ranges from -1 to +1, but the shape of this graph is very similar to sigmoid. So this can also be used for classification in a similar way, and it is also differentiable and continuous, so it can easily be used for neural network backpropagation. So all these three functions can be used. The last option, linear activation function, cannot be used in classification, because if the output is continuous and it is from anything between minus infinity to infinity, then you cannot classify in case of either in case of single or two class problem or in case of multi class problems. So linear activation function cannot be used in the output layer for classification, but all these other three activation functions can be used.
Why we cannot use linear?
Linear activation function, the range of linear activation function is minus infinity to infinity, so it does not restrict the values between any range, and you cannot classify using linear activation functions. If you have only linear activation functions, then you cannot classify which class a certain input will belong to. But in case of, let's say, sigmoid, it is between 0 to 1. So if it is more than half, you can say it is class 1. If it is more less than half, then it is class 0. And in sigmoid, you have multiple output units. Whichever has the highest output softmax value is the class. Similarly, in tan h, range is from -1 to +1. So anything more than 0 is positive class, anything less than 0 is negative class or 0 class. But in case of linear, you cannot classify the points based on the output of the activation function.
Okay.
Now question 5. Threshold functions cannot be used as activation function for hidden layers. So threshold functions are like this: 0, and at some threshold, let's say x naught, it becomes 1. So that is the threshold function, or also called step function. That is the statement that threshold function cannot be used as activation function for hidden layers. The reason says that threshold functions do not introduce non-linearity. There are 4 options whether the statement is correct and also whether the reason is correct or not. Shweta Lakshmi says option A, Muthu Kumaran Iyer says option C. Ansela VM says option C, Anima Naik says option B, Devasis Paramanik says option C, Thanda Akshar says option A. Anantapalli Nagalakshman Kumar says option B. The correct answer is option A. The statement is true, but the reason is false. This is the threshold function. The statement says that threshold function cannot be used as activation function for hidden layers, and this statement is correct, that threshold functions cannot be used as activation functions for hidden units, because there are 2 main reasons. One is that it has only 2 values, 0 and +1. So it does not tell you about the actual value. It tells you that whether it is less than some threshold x naught, let's say, if it is the threshold, it just tells you whether the computed value of the previous layer is less than x naught or not. If it is less than x naught, its output is 0. If it is greater than x naught, its output of the activation function is +1. So it does not really tell you about the continuous value of the last hidden layer. And another thing is that this function is not continuous at this point. So it is 0, suddenly it jumps up to +1. So the function is actually not continuous, and if the function is not continuous, it is certainly not differentiable. And if a function is not continuous and differentiable, then you cannot directly use the backpropagation algorithm. It computes the gradient of the weight values, so it will not be able to compute the gradient values if the function is not continuous and differentiable. So these are the main reasons why this threshold function cannot be used. But the reason stated is that the threshold functions do not introduce nonlinearity. It introduces nonlinearity because this is not a single straight line like this or like this. It is not a single straight line. There are two parts in the threshold activation function. Each part is a straight line in itself. So this is not a linear function. It is a non-linear function composing of two straight line parts. So this
So what were the two reasons? One was because it was telling whether it was less than or greater than. What is the second reason?
Second reason is that it is not continuous and not differentiable.
Okay.
At this threshold point, it is not continuous. It is certainly goes to 1 or 0.
Okay.
So this reason is false, but this statement is correct.
So the reason is false because threshold does have non-linearity.
Yes.
Sir?
Yeah. So initially you might think that it is a linear function, but it is not exactly a one single straight line. There are two straight line parts, isn't it? So less than the threshold, it is a horizontal line 0, and after the threshold it is a horizontal line +1. So there are two straight line parts, but not a single straight line. So it is not a linear function. Similar to ReLU, ReLU looks like this. So ReLU is considered non-linear because there are two straight line parts in ReLU activation function, but as a whole ReLU function is not a linear function because there are two straight lines, two different straight lines. There are parts of the ReLU activation function.
Sir, explain about the first statement, sir.
Statement. Yeah, are you asking about this statement?
As a threshold function cannot be used as a...
Yeah, threshold function cannot be used. So this is correct, that threshold function cannot be used because I just stated the reasons that this function is not continuous, and also it just gives you two values, 0 or 1, which is not really useful for neural network. It cannot process 0 and 1 values. It needs to know more about the actual continuous value. So it cannot be used as activation functions in hidden layers. It does not contain much information about the hidden layers. It just gives you 0 or 1.
Sir, does ReLU function introduces non-linearity in NN?
Yes, ReLU is considered non-linear because there are two straight line parts in ReLU. This is one straight line, this is another straight line, but as a whole ReLU is not a linear function, and it certainly introduces non-linearity.
Okay, thank you.
Question 6. We have a function which takes a two-dimensional input x equals x1 and x2. These are the two features, x1 and x2. Has two parameters, w equals w1, w2, given by f x comma w equals sigma of x1 w1 w2 plus x2. This is the function that it computes, where sigma x is simply the sigmoid function, 1 divided by 1 plus e to the power minus x. We use backpropagation to estimate the right parameter values. We start by setting both the parameters to 0. So basically w1 and w2 both are set to 0 initially, and assume that we are given a training point x1 equals 1, x2 equals 0 and y equals to 5. So, x1 and x2 are the two features, y is the label of that, label or the target value for that. Given this information, answer the next not two questions, it will be one question. What is the value of del f del w2? This is the function fx comma w equals sigma of x1 w1 w2 plus x2, and you have to compute this del f del w2. So, some of you might find this question slightly difficult, so I will show you the steps how to compute it, and it is also slightly lengthy if you try to compute all these derivative values. So, if x comma w is given as sigma of x1 w1 w2 plus x2, and you have to compute del f del w2. So, you have to compute the derivative of this function f with respect to w2. So, to make the calculation easier, let us consider this to be one O2, output of the second layer, pre-activation of the second layer. So, we can write it as sigma of O2. So, the function is simply sigma of O2. Now, if we try to compute del f del w2, which we need to compute here, we can, using chain rule, we can easily write it as this. So, the first part del f del O2, f is sigma of O2, which I have written here. So, del f del O2 is simply the derivative of the sigmoid function, and it is very easy to remember that derivative of the sigmoid function is always this. Sigma into 1 minus sigma, basically at the point O2. So, sigma of O2 into 1 minus sigma of O2. If you simply take this expression of sigmoid and compute the derivative value with respect to x, you can find it out, but it is very convenient if you remember this derivative of sigmoid. It is always sigma into 1 minus sigma, and sigma of O2 basically, because you are computing with respect to O2. So, sigma of O2 into 1 minus sigma of O2. So, the first part, this first part of this derivative can be computed from this. Now, the second part, this one, that del O2 del W2. So, O2 is this whole thing inside this sigma, and if you take derivative with respect to W, simply the sigma of x1 W1 comes out. So, we have computed the two parts of the del f del W2. First part is from here, which is sigma of O2 into 1 minus sigma of O2, and the second part, this one, is this sigma of x1 w1. Now we have all the values. We can compute O2. O2 is this whole thing inside this sigma of x1 w1 plus w2. We know the values of x1 w1 and w2. X1 is given here, x2 is given here, y is not really required. The parameter values initially are 0, so we can put all these values into this expression, and if you compute this, it will be 0.5, 0.5, 0.5. all each of these components would be 0.5.
So the parameters to be 0 is which one, sir, here?
W1 and W2. W1 and W2 are the parameters, or basically the weights of the neural network. So those two values are set to 0 initially. So you have to consider W1, W2 to be 0. So if we put this W1, W2, X1, X2 values, we will be able to compute this del F del W2. So in this question you have to simplify the function slightly so that the differentiation process becomes easier for you, and then you just have to differentiate the whole function f with respect to W2, and you have to apply this chain rule so that the differentiation becomes easier for you to handle. This whole thing is considered as O2, so that we can compute this del F del O2, which is simply the derivative of the sigmoid function. And this computation del O2 del W2 is also very easy, because O2 is simply this, and derivative with respect to W would give you only this part. So this O1 is simply x1 W1. Is it understandable? Okay, moving. Is there any doubt?
So O1 is x1 w1 and O2 is x2 w2, sir.
No, O2 is this whole thing.
Not getting the values.
This whole thing.
How 0.5 is coming after putting the values?
So for example, sigma of O2, if we compute sigma of O2, first you have to compute value of O2. O2 is this whole thing. So put all these values of x1 w1, w2 x2. So first is sigma of x1 into w1. X1 is 1, w1 and w2 are set to 0. So sigma of 0 into w2 is set to 0 plus x2. X2 is also 0. So this is whole thing becomes 0. Sigma of O2 is sigma of 0. Sigma of 0 is half or 0.5. Sigma looks like this. So at 0 it is at 0.5, at infinity it becomes plus 1. So at 0 it is 0.5 or half. So once you compute sigma of O2, you can easily compute 1 minus sigma of O2, which is also 1 minus 0.5, which is 0.5. And sigma of O1 is x1 w1. X1 w1 is x1 is 1, w1 is 0, so 0. So sigma of O1 is sigma of 0, which is 0.5.
Yes, sir, got it.
Now question 7. Which of the following are true when comparing artificial neural networks and support vector machines? ANN error surface has multiple local minima, while SVM error surface has only one minima. Option B says after training, an ANN might land on a different minimum each time when initiated with random weights during each run. Option C says, as shown for perceptron, there are some classes of functions that cannot be learned by an ANN, and SVM can learn a hyperplane for any kind of distribution. Option D says that in training, ANN's error surface is navigated using a gradient descent technique, while SVM's error surface is navigated using convex optimization solvers. So multiple options may be correct. Muthukumaran IS is option C. Okay. Sweta Lakshmi says A, C, D. Megha says option C. Sweta Lakshmi says A, B, D. Okay. What the common answers along with option A. Okay. Devasis says all. So correct options are A, B, D. So the first option says ANN error surface has multiple local minima, while SVM error surface has only one minima. This is correct. So ANN error surface might have multiple local minima points. The error surface might look like this. So there might be multiple local minima points, and it is well known that backpropagation algorithm might get stuck at local minima points. So there are actually multiple local minima points, but which is not the case in case of SVM. In SVM, the only objective is that we want to find out the decision boundary such that it maximizes the margin, and there is only one optimal decision boundary that maximizes the margin. So there is only one minima point in case of SVM error surface. There is only one decision boundary that minimizes the margin. So option A is correct. Option B says after training, an ANN might land on a different minimum each time when initialized with random weights during each run. This is correct, that if you run the ANN or train the ANN with different initial weight values, it might land on a different local minima point. Based on the starting point, it can land on either this minima point or this minima point. So it depends on the initial values of the weights. Option C says, as shown for perceptron, there are some classes of functions that cannot be learned by an ANN. An SVM can learn a hyperplane for any kind of distribution. So ANN can learn any kind of function, whether it's linear, non-linear. It can model any function, and it is also provable that according to this universal approximation theorem, it can approximate any function up to any degree of error. It can approximate any function. You can add more and more hidden layers and more hidden units in each of these hidden layers, and with different kind of non-linear activation functions, you will be able to model any complex function. So option C is not correct. Option D says that in training, ANN's error surface is navigated using a gradient descent technique, while SVM's error surface is navigated using complex optimization solvers. This is correct. So A, B, D, these are the three correct options. Now question 8. You are given the following neural networks which take two binary valued inputs x1 and x2, both belong to 0, 1 binary inputs x1 and x2. So this is x1, this is x2, two features are there, and this plus 1 is the bias term basically. and the activation function is threshold activation, hx equals 1 if x is greater than 0, 0 otherwise. Which of the following logical functions does it compute? So this is the whole neural network. It doesn't contain any hidden layer, just the input layer and the output layer, and the activation function is this step function or threshold function. Hx is 1 if x is greater than 0, 0 otherwise. So which logical function or logic gate does it compute?
Sir, can you once explain this diagram, sir?
So these are the two inputs x1 and x2. Plus 1 is the bias term, and based on the neural network structure, these are the weights: -4, +8, +8. Basically this +8 is multiplied with x1, this +8 is multiplied with x2, this -4 is multiplied with +1, and then these three values are added up.
So that is W1, W2, W3, sir?
Yes, yeah, it is W1, W2, W3 like this. And then you multiply these weight values, and then you take the sum of these three multiplied values, and then this threshold function is applied, that if the sum is greater than 0, then it is then it outputs 1, otherwise it outputs 0.
So the +1 here indicates what, sir?
This is the bias term, basically wx plus b. So this bias term b, if you only take the features x1, x2, then you will not be able to handle any kind of bias or the intercept. So you need to add this +1 in front of all the features. Muthukumaran IS is option C, NAND gate. Devasis is option A, OR. So this it basically computes 8x1 plus 8x2 minus 4. So this minus 4 into plus 1. So this function is computed by this input layer. After that, you are applying this threshold function. So if this quantity is greater than 0, then the output is 1, and if it is less than 0, less than equals to 0, then it outputs 0. This is what it computes. Now this x1 and x2, these two features are binary valued features, 0 and 1. So we can create a truth table for different combinations of values of x1 and x2, and the output, let's say the output is h of x, or even y we can compute it as. So y is basically computation of this, whether it's 1 or 0, based on the based on whether this quantity is greater than 0 or less than equals to 0. So these are the possible values of x1 and x2, because both the features are binary valued features. Now if x1 is 0, x2 is 0, so put 0 here, put 0 here, so we get minus 4. So minus 4 is less than 0, so the output would be 0. Now the second input is x1 is 0, x2 is 1. So x1 is 0, x2 is 1. So x1 is 0, x2 is 1. It would compute 0 plus 8 minus 4, which is 4. So 4 is greater than 0, so output would be 1. Similarly, if it is for the third input 1 and 0, so this is 1, this is 0, so it will be 8 plus 0 minus 4, so it would also be 4. So 4 is greater than 0, so the output would be 1. Now the final input, which is x1 is 1 and y1 is x2 is also 1, so it would be 8 plus 8 minus 4, which is 12. So 12 is greater than 0, so this output would also be 1. So this is the truth table of the function that this neural network computes, and this truth table is exactly same as OR gate. If both the inputs x1 and x2 are 0, then the output is 0, and if at least one of the inputs of x1 and x2 is 1, then the output is 1. So this is simply OR gate. So you have to first find out the expression that this neural network computes, which is this 8x1 plus 8x2 minus 4, and if this whole expression is greater than 0, then it outputs 1. If the whole expression is less than equals to 0, it outputs 0. Now for each combinations of these features x1 and x2, these 4 possible input combinations are there: 0 0 0 1 1 0 1 1. You have to compute the output value, and then you have to find out which gate is it computing. In this case, it is computing OR gate.
Sir, so this is also substitution of values and findings, sir.
This table.
Yes, sir. To substitute the values and to find whether
Yes.
which gate
So
it is.
yes, x1 and x2, you have to substitute these values with 0 0 0 1 1 0 1 1 and compute for each combination of these values what is the output. And we see that only for 0 0 the output is 0, and for all the other 3 combinations it is 1. So it's same as the OR gate. So A OR is the correct answer. Now question 9, choose the correct statement. Multiple options may be correct. MLE is a special case of MAP when prior is uniform distribution. MLE is maximum likelihood estimation, and MAP is maximum a posteriori distribution. A posteriori estimation. So maximum likelihood estimation and maximum a posteriori estimation. First option is MLE is a special case of MAP when prior is a uniform distribution. Option B says MLE acts as regularization for MAP. Option C says MLE is a special case of MAP when prior is a beta distribution. Option D says that MAP acts as regularization for MLE. Multiple options may be correct. Kumaran IAS is option A, C. Devasi says option A, D. Okay. So MLE estimation of parameters theta is mathematically represented as argmax of probability of x given theta. So argmax with respect to theta. So this p of x theta is called the likelihood, and this computes the maximum likelihood. You are maximizing the likelihood with respect to the parameters theta, and this is the MLE estimation. And MAP estimation is mathematically represented as p of x given theta, p of theta with respect to theta. So this is the likelihood, which is same as this, but this p theta is also multiplied with it, which is the prior distribution of the parameters theta. So this likelihood is multiplied with the prior, and then you take the argmax of that with respect to theta to compute the theta MAP, or the maximum a posteriori estimation of the parameters theta. So when this prior distributions p theta is simply 1 by n for each of the data points, each of the parameter values. So this p theta becomes uniform distribution, same for every possible value of theta. Then it simply becomes MLE. You don't need to multiply p of theta in that case. If p of theta is uniform already, then it is not needed to be maximized anymore. It is uniform. It can be treated as a constant. So in that case, it simply becomes this. You can remove this part, p theta. So it becomes same as theta MLE if p theta is uniform distribution. So first option is correct, that MLE is a special case of MAP when prior is a uniform distribution. If this p theta prior becomes uniform, so p theta becomes a constant, so you don't need to maximize it with respect to theta anymore. For every value of theta, it is a constant. So first option is correct, and this also this p theta is multiplied with this likelihood. So this p theta acts as a regularization on the likelihood value. Likelihood is p x given theta. So we can enforce regularization on this likelihood by multiplying this p theta with this likelihood. So if we want the parameter values to be close to 0, which is done in regularization, what you have learned in ridge regression and lasso regression, that we want the parameter values to be as close as to 0. So this p theta would be distribution such that theta values are closer to 0. So in that case, p theta acts as a regularization for this whole MAP estimation. So MAP acts as a regularization for MLE.
So when does it act as regularization, sir?
So if p theta is considered, let's say some normal distribution, it comes from some normal distribution of 0, 1. 0 is the mean and 1 is the variance. So it basically means that these theta values are very close to 0. So if theta values are very close to 0, using this p theta, we can enforce that the theta values, even after computation of this MAP estimation, this whole expression, the theta values remain close to 0. So by and it is only for the theta values, it is not only for theta values to be close to 0, you can create any such distribution for p theta, and it will try to, in the MAP expression, it will try to enforce that constant. So basically by giving p theta like this, that it is a normal distribution with mean 0 and standard deviation 1 or whatever, so it will enforce that the parameter values remain close to 0. So in this way we can regularize this MLE values.
When p theta is They are nearing to 0, sir.
Yep, no, not p theta is nearing to 0. P theta is such that the theta values are close to 0.
Okay, sir.
Theta values are close to 0. So, p theta is some, let us say, Gaussian distribution with mean 0 and standard deviation 1. If the theta values are sampled from this Gaussian distribution 0 with mean 0 and standard deviation 1, in that case most of the theta values would remain close to 0. So, and in regularization we want to enforce that the parameter values remain close to 0. So, by applying a specific kind of prior p theta values, we can regularize this likelihood in MAP estimation, but in MLE estimation or maximum likelihood estimation we do not have any such feature to regularize this theta values. It simply maximizes this p of x given theta, it does not have this p theta expression in it.
So this is applicable only when it is nearing to 0, sir, theta value.
Yes, the regularization, in if regularization is defined as the theta value is close to 0, then in that case it is, but p theta can be chosen in any way. So, if you choose a specific p theta, let us say it comes from a normal distribution of 10 comma 10. So, mean is 10, standard deviation of 10. So, the MAP estimation would try to enforce that most of the theta values remain around 10, mean value remains around 10. So, basically you can design any such p theta prior distribution and try to enforce those restrictions in the MAP estimation. So, A and D are the correct options here. Now, question 10. Suppose you have inputs x, y, z with values -2, 5, -4. So, this is x, y, z and these are the values 2, 5, -4, and you have this neuron q. So, q simply computes x plus y, x plus y is computed here. So, q is x plus y, and this then you have another neuron f which computes the multiplication of q and z. So, q comes from here, z comes from here, and it simply multiplies q into z. So, what is the gradient of f with respect to x, y, z? So, del f del x, del f del y, del f del z you have to compute. So, this question might also seem slightly difficult. So, let me show you the steps. So, from these two expressions we can simplify f as f is q into z and q is x plus y. So, we can simply write it as x plus y into z. So, now I have f in terms of x, y and z, and we need to compute f as a function of x, y, z, because we have to compute its derivative with respect to these three variables x, y, z. So, now del f del x. So, f is this whole expression is f. Now, del f del x is derivative with respect to partial derivative of f with respect to x, and if you compute the partial derivative of f with respect to x, y and z can be considered as constant values. It would simply give you z, and value of z is given here -4. So, it will be -4. Similarly, del f del y. Now, when you compute del f del y, x and z are considered constants, and if x and z are considered constant, then derivative of f with respect to y would simply be z again, and z is equal to -4. Now the last one, del f del z. To compute del f del z, x and y are considered constants. So now if you take the derivative of del f del z with respect to z, it would be x plus y. So I am using this expression in every gradient computation, x plus y into z. So if you take the derivative of this with respect to z, z gets eliminated, x plus y remains, and x plus y is considered constant if we compute the partial derivative of f with respect to z. So x plus y, a value of x plus y can be computed from here. X is minus 5, y is plus 5, so it would be 3. So these are the three values. Del f del x is minus 4, del f del y is minus 4, del f del z is 3.
So basically, given two equations, we are forming a single equation, and using that we are differentiating, sir.
Yes. So you combine these two expressions to model f as a function of x, y and z only. So we are eliminating q from that, so it becomes easier. So f is x plus y into z. Now you take the partial derivative of this x plus y into z with respect to x, y and z separately. So these are the answers. Moving on to question 11. In training a neural network, we notice that the loss does not decrease in the first few starting epochs. What is the reason for this? The learning rate is low, regularization parameter is high, stack at the local minima. All of these could be the reason. Shweta Lakshmi says option D. Muthu Kumar Nair says option D. So the correct answer is option D, that all of this could be the reason, that the learning rate is low. If the learning rate is low, the loss function might not decrease initially, and if the regularization parameter is very high, then the actual loss function will not be utilized that much. So in that case, loss function might not decrease, and it might also get stuck at a local minima. In that case, loss function would not decrease at all. So all of these could be the reason. So option D is the correct answer. So these were the practice questions that I wanted to discuss in this live session. And now if you have any other questions, you can ask me.
So could you explain question 6 once more?
Question 6. So in question 6, f was given, this is f, this whole expression, and to simplify this, I considered this whole thing inside the first sigma as O2. So f becomes sigma of O2. Now I take the derivative of x with respect to W2, which I have to compute here, del f del W2. So the del f del W2 can be computed as del f using chain rule, del f del O2 del O2 del W2, and f is sigma of O2, which I have written here. So now f can be easily differentiated with respect to O2, and this del O2 del W2 can also be easily computed, because O2 I have considered this expression, everything inside the first sigma. Then you just simply compute this del O2 del W2 as well. After that, you have to plug in this x1 x2 and the W1 W2 values. W1 W2 equals to 0 initially. You just have to plug in this x1 x2 W1 W2 values in each of these derivative expressions.
Okay, actually, you till the sigma of O2 I understood. After that, what happens? We have
Did
dou
you
F2.
understand this expression completely?
That I understood. That is okay. And
After that, so
dou
del
F by dou O2 is
del
sigma of O2.
del O2
Uh,
is F is sigma of O2, so it's simply del of sigma O2 del O2, isn't it?
okay, you have written it somewhere, no, no?
This one, can you say this?
Okay,
Yeah, there
okay,
might be a
I'm not.
network problem, I don't know.
No. I don't know where on the screen you are pointing. So
No, I'm
I'm
writing here
seeing the
at
whole screen.
the top.
Top. Okay, that's why I had zoomed there. That's okay. Okay, do if I saw.
This,
That is okay.
so
This is okay.
derivative of sigmoid is always sigmoid
Sigma into
into
1 minus
1
sigma.
minus sigmoid. So that is this part,
Okay.
this whole part,
Okay.
this
Okay.
one.
Okay.
And now this second derivative del O2 del W2 is sigma of O1, the third component in it.
Third. Okay. No, third component means which one is it?
This
Actually,
one,
can
this
you?
one. Using the red tick I have written.
Okay. Okay.
It is becoming a little messy here.
That's what I was not able to understand where it is going. Okay.
So
Now it is okay.
this was computed del F
This
del
you already
O2,
showed how I got.
and then
Yeah.
this is sigma of O1,
Okay. Okay.
because O2 is this whole thing inside the first sigmoid.
Okay.
Oh my, W, sorry, W1 plus x2, this whole thing.
How did we get that actually?
No, that I considered this whole thing inside the first sigma as O2 for easier computation.
No, but actually that is not the equation. That's not the equation that is given on the top. No, O2 is sigma of W
Yeah,
x1
sigma of
W1
x1, sorry, sigma of
x1
x1
W1.
w1 w2 plus x2. Yes,
That is what. That's what.
now
Okay.
you
Now okay.
compute del O2 del w2 for this. So so it simply becomes sigma of x1 w1.
Correct. Okay. Okay.
So x1 w1 is O2, but you can easily compute x1 is given here as 1 and w1 is 0, so sigma of 0 basically.
But that how did that step? Can you please repeat once more? I did not understand. Sigma of x1 W1. How it becomes sigma of 0?
X1 is given as 1 in the question,
Oh. Okay.
and
Okay.
w1 is 0, w1
Okay. So
w2 as
okay.
0, so
Okay.
sigma of
Okay.
0.
Okay. Now that is so. The answer is sigma of 0.
Sigma of 0 for this del O2 del W2. Now you have to multiply all three parts,
Okay.
so each of them becomes 0.5 0.5 0.5. You can simply
Now,
plug in all these values.
how did we get that actually?
Sigma of O2, so this O2 is computed here. O2 is yeah, you can plug in all the values again, x1 w1 w2 x2. It becomes O2 is 0, so sigma of O2 is sigma of 0. Sigma of 0 is 0.5, so 1 minus sigma of O2 is also 0.5.
So it's a sigmoid function. Okay.
Yeah,
And 1 minus sigma 2 is also 1 minus
sigma
point
O2
five,
is
which is
also
0.5.
0.5, and third one is also 0.5, so
Yeah,
all
okay.
three
Now I
becomes
got.
0.5.
Okay, now, okay. Somebody else had asked some other question. One more question I was having a doubt. That was question 9.
Question 9.
No, not actually 9. The thing is, after you answer the other person's question, could you please explain that likelihood, that parameter estimation thing? That I did not understand it fully, I think.
Whole parameter estimation I cannot discuss
No,
right now.
just an overview. After somebody else had asked a question 11 doubt or something, after that you can, I'll ask you this.
Question 11. Question 11 is, I mean,
That is okay for me. That's okay for me. But somebody I think had
yeah,
given a
I've
message.
seen question 11 is simply loss function is not decreasing. There might be many reasons. First is that if learning rate is low, question it might not decrease. Regularization parameter is also high. In that case, loss becomes much lesser than the regularization loss, and it might get stuck at a local minima, then the loss would remain stuck there. So all three reasons could be there.
Sir,
Okay, now
can we leave if you don't have any doubts?
Yeah, you can leave.
actually, sir, that parameter estimation, no, how many techniques are there totally? MLE, MAP, and
Yeah, mostly MLE and MAP are used.
okay, one or two more were mentioned. No, that's all. Only these two we have to see.
No, I don't exactly remember. There are 3 videos. I don't exactly remember all the methods, but
Okay.
mainly maximum likelihood estimation and maximum a posteriori
So
estimation
what
are
we are
used.
doing for MLE and what we are doing for MAP? Can you just?
So we
I
want
went.
to find out the distribution of the data x. In this case, you don't have to bother about y, the levels or the target values. We want to model
Okay.
from where the data is coming. What is the underlying distribution of the data points x?
Okay. Okay.
So and we want to find out the parameters theta. If let's say it is
Okay.
a Gaussian distribution, so parameters would be mu and sigma. If it is some Bernoulli distribution, it would be parameter would be p, like that for different
Theta means the parameter of the distribution.
distribution. If we already
Okay.
assume that it is coming from a Gaussian distribution, so parameters are only mu and sigma. So we want to
Okay.
find
Okay.
out, estimate the values of this mu and sigma
Okay. Okay. That is a parameter estimation.
parameters. So
Now,
now you compute this likelihood
mm,
likelihood p of x given theta.
mm,
That is called the likelihood, that for a given theta value, that is mu and sigma value for Gaussian, what is the likelihood of a certain point x. That is simply for
Okay.
Gaussian, you have this expression 1 divided by root 2 pi sigma square e to the power something. That is the p of x given theta for Gaussian distribution. So
Okay.
you compute for every point, and you take
so
the
which is likelihood P of x given theta is called likelihood.
yeah, p of x given theta is the likelihood, and in MLE you want to maximize this likelihood with respect to theta. You want to find out the values of theta for which this likelihood is maximized.
So how do we do that?
The maximization can be done in any optimization process. Either if you are able to compute the derivative, you just compute the derivative with respect to theta, equate it to 0, find out the parameters. If it is a if it is an easy distribution like Gaussian, you have only two parameters mu sigma, take the derivative with respect to mu and sigma, find out the value, like
So
that.
we know actually what is theta given x, sir? Or we don't know that also.
Theta given x we don't know.
So we don't know theta given x, but we know x given theta.
We this each of these point values would be given to that x1 x2 up to xn n points should be given to us, and we know that the underlying distribution is Gaussian, but we don't know the parameter values mu and sigma.
We don't know theta, but we know
Points are given, and the parameter the distribution is known that it is Gaussian, but the parameters are not known. Mu and sigma are not known.
Okay.
So you for
Okay.
each of these points x1 x2 up to xn, you compute this Gaussian distribution values. So mu and sigma would remain in the expression because you don't know the values of mu and
No,
sigma.
we already know we know the data point and we don't know the parameters of distribution.
Yes.
So how can we compute that equation of the Gaussian without knowing the parameters of distribution?
Parameters would remain in the Gaussian so the Gaussian equation is something like this.
1 by root
The
of
constant part is not required. I mean, it is required, but I'm not interested in that. So
Okay.
it would simply be
X
xi minus
the
mu
whole
square divided by 2 sigma squared.
2 sigma square.
So xi values I know, I will put those values. Y sigma I don't know. So y sigma would remain in the expression, isn't it?
Y sigma.
Sorry,
Y means-
sigma mu and sigma. Sorry, mu and sigma
Okay.
would remain in the expression, and I will take the derivative of that. Derivative of with respect to mu, derivative of this with respect to all sigma also. In the like this we can compute the then equate it to 0.
Okay, well
This
then
is-
when we do that, we are assuming that it is maximum.
Yeah,
It
this
could be minimum also, no? When we equate to 0.
no, we want to maximize the likelihood. Yeah, it could also
Yeah,
be.
but actually
Yeah,
when you
in
equate
that
to
case, you
zero,
have
it
to
could
take
be
the
minimum.
second order derivative also to.
We are doing
check.
that also.
Yeah, I don't remember whether it is taught in the class in that way or not.
I know, I
But
don't know because I don't remember exactly because when I saw it, I was not able to answer this question also. That's why I asked you.
no, yeah, it
So
can
from
also
here,
be minima, but the expressions are such that I think they, if you simply equate it to 0, you mostly get the maximum points only. But yeah, if you want to be on the safer side, you have to take the second order derivative, and if it is less than 0, then it is maximized.
okay, so we are given some data points, and using those data points, we are finding out x given theta
Hmm.
as equations in terms of mu and sigma,
Yes.
and we are equating each one to 0.
Yeah,
And
take
then
the
we are finding
derivative
out
with respect to the
values.
parameters and equate it to 0. Yeah.
So we'll get different equations for the with the parameters as mu and sigma.
Hmm.
We are going to use simultaneous equations to solve it
No,
and find the values.
there is only yeah, there will be two equations for two derivatives with respect to mu and with respect to
No, but
sigma.
you are given 10 points. You are given 10 points. You don't know what your mu and sigma is.
Yes.
So, what we do is we will be finding out the expression for each of the 10 points.
Then
And then we
multiply
will be
them.
getting some differential
Total,
of that.
the total likelihood would be multiplication of each of the points likelihood values.
Okay, that assumption is there. Okay, so
Yeah,
because
this
of
is
that, we'll
simply
get the total.
product of p of xi given theta for I equals 1 to n. This is the total
So,
likelihood of all the points, or the total likelihood of the whole data set.
so that is all that we are finding. We are only finding the total likelihood. And where are we using the differential now?
So each individual px I given theta would be a Gaussian distribution. You plug in the values there in the Gaussian distribution expression.
No. Can you express that last point? Could you please come again? I did not understand.
P pxi
No,
given,
no. Actually, we are given 10 data points, and we know that it's a Gaussian distribution. We don't know mean and sigma. So, with that, can you tell me how we are going to use MLE to estimate mu and sigma?
yeah, so for each point pxi given theta, you compute pxi given theta. It is simply that 1
So
divided
we
by
don't know
root 2
theta
pi.
also. We don't know theta also. We just
Theta
know the
is mu
x's.
and sigma, that is considered as variables initially. It would
Yeah,
be
yeah, yeah.
in an
So for
expression of mu and sigma. Xi values are known,
and
mu and
okay.
sigma are not known.
So
It is
we are
something like
getting
that
10
of mu and sigma
equations.
would remain there.
We are getting 10 equations in terms of x minus
10,
mu the
not
whole
10
square by.
equations, it would be multiplication of each of the points. You have to multiply the likelihoods of each of the points, and generally log
No,
likelihood is
see,
used.
the likelihood also we are going to get only in terms of mu and sigma, no? Because we don't know what mu is and what sigma is.
Yeah,
How
mu
we
and
will get
sigma
the
would
likelihood?
what I'm telling is that xi's would not remain in the expression, only mu and sigmas would remain in the expression for
So if
each
you have
point
10
xi.
points, you're going to get an equation in terms of mu raised to 10 by sigma raised to 20. Yeah?
Yeah, like that. So to
So,
you multiply
like
all
that
the
we
points.
get.
That is why generally log likelihood is used. You take the log of that, so that you get a summation something. Log of
Okay.
product. So you get a summation over the whole expression, not multiplication. So it becomes easier for you. So it is not
So
possible to discuss the whole, all three videos content in this
no. I am
particular
not
session.
asking for that. Just to understand, because I that video we can also see. No, now this one you just to understand what it was. Now you told me that we are getting an equation. Now from the equation, how do we find out that mu and sigma in one word or two
So
words?
you
You
get
can tell
one
what
likelihood
process.
expression which contains mu and
Huh?
sigma. Now take the derivative of that expression with respect to mu. Take the derivative of that expression with respect to sigma. So you
Okay.
get two equations,
Yeah.
two the simultaneous equations. You have to solve those equations in that
Are
case.
using that we will be finding out the values of mu and sigma.
Yes.
You are telling. Okay.
And there are other methods also, like expectation maximization. That is an iterative method, not exactly like differentiating. EM
Okay.
algorithm, I don't know whether that is covered in that
No, it
parameter
was not
estimation or
covered,
not.
but
I
it
don't
was
know.
not
So
covered. It
there are
was
other
not covered.
methods also to find out the optimal values of the parameters, but that
That
is
is
the
what is there.
easiest method. What?
Okay, but can you mention 2 or 3 other methods also just because for the exam's sake?
Mm, no, EM method I remember, but I don't remember exactly the
Okay,
algorithm completely.
equation. Okay.
I don't remember
Then
any
what
other
about
method.
MLE? Now you have told about MLE. Now can you tell about MAP and how it becomes
Map,
a
the
regularization?
process remains exactly same. You just multiply this p theta,
Ah,
this p theta uh, with the likelihood. So the p theta basically tells you a prior information regarding the values of theta. How would you
okay.
sample the values of theta?
Okay.
So
So that's why it is becoming a regularization for
yeah, if
MLE
you enforce
because
that the
because you
thi-
are taking log likelihood, it becomes a plus term.
so if you you can enforce different constants or the values of theta using this prior. So, if you say that the theta values come from this normal distribution of mean 0, standard deviation 1, that means the parameter values are very small, would remain very small even after the maximization. So, that acts as a regularization.
Okay, so how it will act as a regular, but we don't know. Finally, the value need not be between 0 and 1.
No, that prior, if prior is known, then only you can apply it. Prior might also be known, that the mu, we don't exactly know the values of mu and sigma, but we know that the values of mu and sigma are sampled from some distribution. It can be Gaussian, it can be Bernoulli, it can be any other beta distribution. It is known that it is sampled from some distribution.
Okay, that information I got, but still I did not understand how map acts as a regularization for MLE when the prior is known.
This is what I told, just that this if this constant is there, that p theta values come from mean Gaussian distribution of mean 0 and very small standard deviation of, let us say, 0.1 only. 0.1.
Okay, that is also given to us. Okay.
Yeah, it is known to me. So, that means theta values are very close to 0. So, now if I multiply it here, so it tries to enforce that constant, that theta values are very close to 0, would remain very close to 0.
Okay. So, that is why it's called regularization.
Yes.
And what about the first option? It's a special case of map when prior is a uniform distribution.
So, if p theta is uniform distribution for every value, every possible value of theta, it acts as a constant. So, you don't need to put it inside this argmax expression. It is a constant in that case.
So, how does MLE become a special case of map?
If p theta is 1 by n for all possible values of n, if there are n possible values of theta, it is 1 by n. So, it is a constant with respect to theta.
Yeah.
So, we can simply remove it from this expression. It simply becomes argmax of the likelihood px given theta, because p theta is now a constant to me, because it is an uniform distribution.
Okay.
So, this whole expression is same as this MLE.
Okay, thanks. Okay, thank you.
Okay, if there are no other questions or queries, then we can end this live session now.
Okay, thank you, sir. Thanks.
Thank you. Thank you everyone for joining.
Thank you, sir.